This is an Archer screencast for the Reveal application. Reveal is a performance analysis tool supported by Cray that guides you in improving the performance of a cray-compiled application code. Specifically, Reveal will analyze the loops within your code and identify which ones are less than fully optimized and why. In addition, Reveal can gather performance statistics that rank the loops according to length of execution time, thereby showing you the best places in the source code to apply optimizations. An overview of Reveal can be found in this Cray document using Cray performance measurement and analysis tools. Alternatively, there is a Cray Reveal webinar that's available online that gives a much more detailed review of the Reveal tool. The purpose of this screencast, however, is to simply give a straightforward example of how a researcher might run Reveal with their MPI application code, and thereby show how to make the code run faster, and also how to add parallelism by introducing OpenMP directives. Now, my example MPI code that I'm using for the purposes of this screencast is called Layer3D. It's a three-dimensional Lagrangian remap code for magneto-hydrodynamic simulations. That's what MHD stands for. It's open source and it can be downloaded from this CCP Forge website that's hosted at Warwick University. Now, what Lagrangian remap means is the code it simulates a magnetized plasma as a single fluid, and at every time step the grid moves with the plasma. The plasma properties are updated and then remapped back to the original fixed Eulerian grid, and then the simulation moves on to the next time step. This is what is meant by Lagrangian remap. In this screencast, I will actually be using a customized version of Layer3D. It was used to generate the results for this academic paper. The actual simulation discussed here is of a perturbed magnetic flux tube, and these are the modelled magneto-hydrodynamic equations. So we have a force equation, which is the second one, and that has various terms such as a pressure force and also a Lorentz force. And then we have the induction equation, which just tells us how the magnetic field changes with time, and that will have a resistivity term on the right here. It's indicated by eta. So now that I've just introduced briefly as possible the MPI application code, I'll now move on with the screencast. The Reveal application itself, we will run it on one of the logging nodes of the Archer machine. So I'm going to use an SSH agent to set up my Archer session first of all, and to do that I had to specify a config file. So the host I'm using is Archer, and because Reveal uses a graphical user interface, I need to have set the forward x11 and forward x11 trusted options so that that user interface will display within my Archer session window. So those two options are basically the equivalent of the -XY options that you might use on the command line when running the SSH command. So I'm going to log into Archer now. And the Layer3D source code I've set up on /work. There it is. So I should show you my module environment. It's basically just the default. So I have the Cray programming environment loaded, and in order to run Reveal, I need to first load the perf tools module. Module load. There you go. So I have version 6.2.2. So perf tools is also required for a couple of other utilities that I will use, pat build and pat report. So what Reveal what you need to do first of all to use Reveal is to compile your source code in various ways. The first way is to generate a program library. So that's this option here, -h pl equals layer3d.pl, which is just the name of the folder that will contain the library. And the library is basically a set of analysis files for each source code file, and it tells me where optimizations have been applied and where optimizations could not be applied. There's also another option, this -h profile generate, and I'll be using that to prepare an executable that, when instrumented, will generate loop performance statistics. But first, I'll compile the code so to generate the program library. Clean make option equals reveal prog lib. Okay, so this will take a minute or two to compile. But when it's done so, we can then run Reveal, pass it the program library, and then it will basically show us the source code, but the source code will be annotated to tell us where vectorizations couldn't take place. Okay, we're at the linking stage. This shouldn't be much longer. Great. So there's the program library, and we can look inside and see that we have a number of files for every source code file. You saw when it compiled that we were compiling X-remap and Y-remap and so on. So each of these files basically contains a different set of analysis of the source code. Right, so we can run Reveal. I'll enlarge this window. Now the main application file in Layer 3D, where the simulation starts, is in layer3d.f90, and I'll scroll down to the main application loop. So each iteration is one time step in the simulation. And you notice on the left hand side there is a column of annotations, character annotations. L stands for loop, and !I means that this particular call couldn't be inlined. But we're going to focus on the main function within this loop, which is the Lagrangian step, which is where when the plasma, when the grid moves with the plasma. So that's defined in this source code file Lagrange.f90, and then this function in turn calls the predictor corrector step. And you will see as we scroll down here, we've got some more character annotations, and a useful feature from the help menu is something called the loop mark legend, which basically brings up all of the annotations, and you can quickly find out what a particular letter means. That's a useful feature. But I'm going to scroll down to a particular part of this subroutine, which is here. Now this is a set of nested loops, one for each dimension. And you can see in the info window it tells me that a particular loop couldn't be vectorized because of a better candidate was found at line 249. But when we go to line 249, that says that this loop in the x dimension now couldn't be vectorized because of a potential hazard in conditional code on line 475. So this may be an improvement we can make right away and make the code run faster. So what does this this set of nested loops, what does it do? So it works out the terms in the MHD force equation. So we have the pressure force here. It's being calculated, and we scroll down further. There are the viscosity force. Now we're working out the currents, Jx, Jy, and Jz, and that's in preparation for working out the Lorentz forces. Now this potential hazard was at line 475, and here it is. Here's the conditional code that's preventing the vectorization. Now these terms here, W1 and W2, what those are basically the kinetic energy for a particular cell. So we have the velocity squared multiplied by some mass term. So what this set of nested loops does is it basically traverses the entire grid in calculating the force terms, and also working out how the kinetic energy changes over the time step, and that's what that subtraction does, W2 minus W1. But if a cell intersects a boundary, and what that means is that the boundary runs through the center of the cell, so half of the cell is in the grid, half is outside, we need to divide the kinetic energy by a factor of 2, because actually only half of the mass in the cell is actually within the grid. And this code is quite easy to refactor, actually, to remove the expressions for W1 and W2 and take them outside of the conditional statement. But before I do that, we'll run the code as is in order to produce a baseline loop performance. Okay, so now we're going to close the reveal application and then recompile the Layer3D source code a second time. But this time we'll compile it with the prof_gen option, and so I'll just do a make clean. So I said prof_gen. What I meant was profile_generate. That's the -h option. So what we're doing is, was before we compiled the code to produce a program library, now we're compiling the code so that when the executable is instrumented, we'll also capture all of the loop performance statistics. So that means after this there will be an additional step where I'll have to use pat build to instrument the generated exe. Okay, nearly finished. So there it is. So go into the bin directory. That's where the executable was written to, and we can run pat build with two options, a W and a V. The W enables tracing, so that when the app executes, it can follow which loops were called and thereby collect the runtime performance data. And the V just indicates verbose output. So this will take a few seconds, and at the end it just outputs a summary of the memory used. And there we go. So now that we have an instrumented exe, the Layer 3D plus PAT, we're ready to submit the job, and then we could get the baseline data for the loop performance. And the job will be submitted using a script such as this one. So here I've just selected 3 nodes, and I'm using only 64, so not all the nodes aren't fully utilized. And notice that I'm using the instrumented exe on the AP run command line. Now I've already submitted this job and obtained the output data. That's where I'm going to go now. So 2 files were produced, standard output and standard error. I'll show you what's in the standard error one. It's not actually an error, it's just a message from cray-pat that tells us that the experiment data file was created. And the output file itself, which contains actual output from Layer 3D, that gives us the runtime. So that's nearly 16 minutes and 50 seconds. And when we go back to that nested loop structure that I pointed out, that couldn't be vectorized because of the potential hazard. Once that's corrected, then we should see that runtime come down. So we have the experiment data file, .xf file, and in order to run that through Reveal, we first need to run pat report, and we run it just like so. That quite a bit of output is generated, so we'll just send that to a text file. There we go, and we can have a look inside there. So just go to the top, and we've got the basic information, the number of calls that were used, 64, and we should get to a table. So that breaks down the runtime according to name of subroutine. And then we scroll a bit further down, we have the table for all the various loops within the source code. So right at the very top we've got the main application loop, where most of the time is spent. That's not surprising. But then we can see which loops that are called from within the internals of Layer 3D, such as the Lagrangian step. So we've got this loop predictor corrector step. So that's on line 245 to 247, 249, and those are the loops that we were looking at earlier. So we can see that those are fairly expensive compared to the other loops at least, and so it would be a good place to try and do some work and try and change the code so that those loops can be vectorized. And that's something that I've already done, and I can just show you in this code. And that's in here. So these are the loops that I mentioned earlier. So before, the W2 and W1 variables were being set up inside these conditional statements, and I've added an extra variable called bd_count, which is just a boundary count, which counts the number of boundaries that a particular cell intersects, and then uses that value to work out which factor should be used to reduce the kinetic energy. And so now that W2 and W1 have been moved outside those conditional statements, this code should be vectorizable. The loops rather should be vectorizable. And I'll just do a bit of cleanup in here. I've already done some work in that I've run the code with this refactored loop so that it can be vectorized, and so I then also submitted the job with the profgen option used to compile the code. So we can see what the improvement in runtime was. I just look in this layer 3D output file. And you can see it's come down to around 15 minutes, whereas before it was 16 minutes and 50 seconds. So that's around about a 10% improvement. So now the various. So what I've done here with this new version of layer 3D, this slightly new version, is that I created a program library, and I also then went ahead and ran it with the profile generate option on, then created the experiment data file, this .xf, then did a pat report to get the .ap2 file, and now we can have a look at those within Reveal, and we can just pass everything on the command line. Whereas before I loaded the performance data from within Reveal from using a file menu option from the file menu. So there we go. We've already got the loop performance data loaded. And if we look at where the set of nested loops, the ones that work out the terms in the force equation, here they are, and you can see that the character annotations on the left hand side have changed a little bit. So now the loops have been vectorized, and there's an additional message. I just enlarge the window so you can see it. Also just show you that this is indeed the refactored code. There you go, with the boundary counter. So what that's saying, the little red circle, which gives a warning, it's saying due to lack of hardware resource, basically, not all of the vector registers required there wasn't a sufficient number of them on the hardware, so 5 of them had to be forced to memory. It might be possible to change that by making the loop less complex, by splitting it up, but then you would have more than one loop when previously you had one, so that would take longer to run anyway. But looking on the left hand side, we can see that the runtime for that loop has definitely come down, and then also for the outer loops as well. It's around about 37 seconds, whereas before it was around, I think it was almost twice that, it was around 70 seconds. Last part of this screencast, we will look at how to add OpenMP directives. So from within Reveal, we'll run a scoping tool, and here we are under the View menu, and we'll decide that we'll add all loops initially, but then we'll apply a filter. So we're only interested in those loops that take more than 20 seconds to execute. So we've applied the filter there. So just looking at which loops have been selected from within the Legrand.f90 source code file. Then we can start the scoping. So what scoping means is basically looking at where there are opportunities for using OpenMP. And Reveal goes further and tells you or gives you its best advice as to which OpenMP directives to use. So you'll notice that a few things have changed in this window here. We've got some icons going along the right for each of the loops. Where we have a red circle, that means that OpenMP directives couldn't be applied, or Reveal couldn't find a way to do it. Where we have a green square, that means Reveal had no problem in deciding the OpenMP directives to put in. And where we have a green square with an orange triangle, that means that yes, Reveal could add OpenMP directives, but it also has some warnings to show as well. So we can have a look at some of these. And in this particular area, so at the loop at this line number 95946, we can add OpenMP directives, and this is within the eta_calc subroutine. And what eta is basically the resistivity, which is being calculated in this subroutine for every cell over the grid. I should show you the other window, which is the OpenMP scoping window, and the content of that window will change as you select various loops. So here we see you have lots of errors. You couldn't find the set of OpenMP directives that would work. But when we go back to the loop within the eta_calc subroutine, it gives a suggestion, which we can see when we click on the show directive, the option, and we can see here it is, and we can either copy it and paste it into our source code later, or we can just insert the OpenMP directives right away, which is what we've done here. And then at this point, Reveal has only saved it to a local copy, to its own copy of the source code. To actually make sure it's in the source code file proper, we click on Save and then select Yes. So it's in there, and we can then close Reveal and just double check that it has found its way there, and we can go. There it is. Those are the OpenMP directives that we've just added. Now we can compile this code without using instrumentation, actually, which I've already done. And then when we run, it should execute successfully. And when we have a look at the runtime, I should also first just show you that it was necessary also to change the submission script because we're using OpenMP. So we have more than one thread per MPI process, for example. So now I've specified 64 MPI processes that each have 3 threads. 64 times 3 is the same as 8 times 8 times 3, which equals 24 times 8. So we have fully utilized nodes. And let's look at the outputs, see what they're on. And the runtime has come down by a lot now. So with the refactor code, it was around 15 minutes. It's now come down to almost 9 minutes. Well, that's not surprising. We're using more hardware resources, and also this executable is uninstrumented. But this just shows that Reveal can be used to almost automatically choose the OpenMP directives that you can use for the loops in your code, and thereby reduce the runtime. Thank you for listening. This is the end of the screencast.